Jai Hind, welcome to the course Network Analysis and Synthesis, and today we are going to discuss some examples using the node analysis to solve a circuit in graph theory. So, yesterday we discussed the theory about the node analysis and we carried out one examples. Today we will discuss some more examples on the node analysis. So, for the network shown below, the network is like this. Network is like this. It is one voltage source of 1 volt, then 1 ohm impedance, then 3 Henry, 4 Henry, then there is, so here there is dot, here dot we have and dot here we have, okay. There is mutual inductance between these two, which is 1 Henry. So, M is equal to 1 H. Okay, this is 2 farad and this is okay, this much. Now, branch numbering is also given. If it is not, then you have to number it. So, this is branch 1, this is branch 2, this is branch 3 and this is branch 4, okay. And nodes are also given. So, this is node number 1, this is node number 2 and this is node number 3. So, we know that in the node analysis we take a reference node. So, this much information is also given. And it is also given the direction of the current. So, direction of current is like this. Okay. What you have to do? Find the F fundamental cut set admittance matrix and also solve for the node voltages. So, there are two problems. One is to find YC, which is fundamental cut set admittance matrix, which is equal to QF is the fundamental cut set matrix, YB and QF transpose. This is the one question that you have to answer. And the second is solve for the node voltages. So, you have to find this equilibrium equation. IN is YN VN. So, for this particular example, you have to find out cut set admittance matrix, which is fundamental cut set matrix into branch admittance matrix into transpose of the fundamental cut set matrix. And in the second, you have to find the equilibrium equation node current equal to node admittance matrix into voltage, node voltage, okay. Now, we can see that the network is given in resistor, then inductor and capacitor in ohms, farad and Henry. So, first job is to convert the circuit in S domain. You have to do it, okay. So, first and foremost you have to convert this circuit into S domain. It will be like this. So, it is 3. So, 3 XL is, remember XL is j omega L and XC is 1 by j omega C. So, in the place of j omega we can write S. So, it is j omega L SL. So, 3S. This is 4, so 4s, and mutual inductance between these two. So M is equal to, it is 1 Henry, so it is 1s. So at S. Okay. Then you have to convert this capacitor. So 1 by X is equal to 1 by S, and C is how much? It is 2 farad. So S into 2, so it is twice S. Okay. So this is twice S. Okay. And then we do the branch numbering. This is branch number 1, this is 1 ohm, this is 3s, this is your node, this is node 1, this is node 2, this is, and this is the node 3. Branch 1, branch, this is the branch 2, branch 3, and branch 4. Okay. So first you have to convert this circuit into S domain if they are in the Henry, farad and ohm. Second step is you have to find this one. So for this we need, so QF is, what is QF? QF is fundamental cut set matrix. Okay. So fundamental cut set matrix is applicable to a tree of a graph. So first you have to draw the oriented graph and take a tree. So now the oriented graph is of this is like this. This is 1 ohm. So this is the branch 1. So there are, this is node 1, then node 2, and node 3. Okay. So between node 1 and 2, this is the branch 2. So this is 2. Then 1 and 3. Then 1 and 3. There is a branch 1 and direction is, this is branch 1. This is branch 2. Okay. Branch 2 to 3, there is, this is 4. So this is 4. And the direction of current is this. So it is from 2 to 3. And 1 to 3. 1 to 3 is branch 3. And orientation. So this is the oriented graph. Oriented graph. Okay. So we have drawn oriented graph. Now take a tree. So here I am taking 2 and 4. 2 and 4 as a tree branches. So 2 and 4 are the tree branches. So this is your node 2. So this is your 4. This is your 2. And this is, these are the 1 and 3 are the links. Okay. So 1 and 3 are links and the direction is like this. So this is 1 and this is 3. Now, yeah, I can write here 2 and 4 as tree branches, because it is not given in the examples. So you can take 2 and 4 or somebody take other branches as a tree branches. So first select a tree. Now find the fundamental cut set. So we know that fundamental cut set is a combination of twig and unique set of links, and the orientation is along the twigs. So this is C4, and one is like this, C2. So there are 2 twigs. So there are 2 fundamental cut set. Then we can write the matrix straight way. So this is C2 and this is C4. So number of rows in a fundamental cut set matrix is equal to the number of fundamental cut sets. There are 2 fundamental cut sets, so the 2 rows, and the number of column will equal to the number of branches. So there are 4 branches. Now C2. C2 is a combination of 1, 2 and 3, and we know that orientation of 1 is just opposite to the orientation of 2. So, it is -1, this is 1 and this is 1 and this is 0. In C4, 1, 4 and 3. So, 1 and 4, 1 is just opposite. So, this is -1 and this is 0, this is 1 and 1. So, this is QF. So, once you have written the QF, then we can take the QF transpose. So, QF transpose is -1, 1, 1, 0, then -1, 0, 1, 1. Okay, we can, okay. So, this much, and what we have to do, we have to find this one. You have to find this YC is equal to QF, YB and QF transpose. This you have to. So, we have got QF and QF transpose. Now, find the YB. So, YB we can. So, basically impedance is given. So, YB is nothing but it is inverse of impedance matrix. So, write the impedance matrix ZB and then invert it to get the YB. So, we first write the ZB. So, ZB is, it is a square matrix 4 by 4 because there are 4 branches. So, 1, 2, 3, 4, 1, 2, 3, 4. Okay. So, if we can see that in the branch number 1, there is 1 ohm impedance and there is no coupling with other branches. So, it will be 0. Now, come to the branch number 2. The branch number 2, no coupling with 1, so it is 0. The self impedance of the branch 2 is 3s, so it is here 3s. Now, it is coupling with the 3, so it is this is 1s, this is s. Okay. Now, one more question, whether this will be the plus sign or minus sign. Suppose there are two windings, and here is the dot and current is, so current is leaving in the both the coils, so it is the flux direction will be positive. Suppose it is like this and it is like this, and current is entering in this coil and this coil leaving, so it is minus. So, this way we can take the direction of this mutual inductance. Okay. There is no coupling with branch 4, then 3 1 no coupling 0, 3 2 coupling is there, so s, and 3 3 is 4s, so it is 4s, this is 0. Now, no coupling and the self impedance is 2isf 1 by 2s, so it is 1 by 2s. So, this is ZB. So, this is ZB. Now, you have to find the YB. So, what you have to do, you have to just invert this one. Take the inverse of this. Take the inverse of this matrix. Okay. And take the inverse of this. Take the inverse of this one inverse, so 1, and this is a 2 by 2 matrix. So, you have to invert this matrix, this one. Okay. And you have to invert this. So, YB will be, I am writing YB directly, I can write here. So, YB is coming like this, 1 2 3 4, 1 2 3 4. So, YB is coming like this, it is 1 0 0 0, then 4 0, 4 by 11s. you can check 4 by 11s minus 1 by 11s, then 0 minus 1 by 11s, 3 by 11s, and this is also 0, 0, 0, 0 and 2s. So this way we can, if the impedance is given, you have to take the admittance. In the last lecture the admittance was given, so straight we can write the YB. Here the impedance is given, so we have to take the inverse of that ZB, and this way we can get. Now you can multiply YC is equal to QF YB and QF transpose. So this on multiplication we are getting this. So I am writing the final result, we can check, nothing, this simple matrix multiplication. Then 1 plus 2 by 11s, 1 plus 2 by 11s and 1 plus 3 by 11s plus 2s. So this is your YC, this is YC. So this way we can get the YC. So first answer is YC, and we have to find this matrix. Now the second is, now come to the second one. Second one is, second part of this problem was to find IN is equal to YN VN, and YN is node admittance matrix is, what is node admittance matrix? It is A matrix into YB into A transpose. So here you have to write the A matrix. So I am just calling the graph of this network. So graph of this network was like this. This is your 2 node, this is 3 node, this is branch number 2, this is a branch number 3, and this is a branch number 1. This is a branch number 1. Okay. This is branch number 1. This is 1. This is 1, this is 2, this is 3, and this is 4. This is 4. And this is, they are the nodes. And this is node number 1. So how many nodes are there? There are 3 nodes. So first write the A. A means 1, 2, 3. 1, 2, 3, 1, 2, 3, 4. Okay. So branch number 1 is in between 1 and 3, and it is approaching 1, so minus 1, 1, 0. Branch number 2 is in between 1 and 2, it is approaching 2, so 2 is minus, 1 is plus, and 3 is 0. Now branch number 3 is in between 1 and 3, so 1, 0, minus 1, and 4 is 2 and 3, 2 and 3, so 2 away from 2, so 1, minus 1 and 0. So this is A. Now take the A matrix. A matrix means eliminate this row, eliminate. So A is 1, 2, then minus 1, 1, 1, 0, then 0, minus 1, 0, 1. Okay. So A matrix minus 1, 1, 1, 0, 0, minus 1, 0, 1. Now take the A transpose. Minus 1, 1, 1, 0, 0, minus 1, 0, 1. Okay. And YB we have calculated in the previous slide. So YB is coming, I am writing here directly. What is IV? So IV is 1, it is 1, 2, 3, 4, 1, 2, 3, 4, 4 by 4. So IB I am writing here 1, 0, 0, 0, then it is 0, 0, 0. Now it is 4 by 11s. You can check, okay. Simple 1 by 11s minus 1 by 11s, 3 by 11s. This is 0, this is 0, 0, 0, 2s. So yn is A, YB and A transpose, and this is reduced incidence matrix. We discussed in detail in the previous lecture. So this on multiplication of these three matrices A, YB and A transpose, we are getting Yn. So Yn is coming this one 1 plus 5 by 11s minus 3 by 11s minus 3 by 11s. This is one element, okay, and this is 4 by 11s plus 2s. This is, so it is 2 by 2 matrix. Now find In. If you remember in the previous lecture we got the derivation of this. So it is A YB Vs plus AIS, okay. So and there is no current source, in this IS is equal to 0. So In is equal to minus A YB Vs, and Vs we can write, and Vs is a 1 0 0 0, because this is the 1 volt in branch 1, branch number 1, branch 1, okay. So this is 1 volt and it is leaving the, we can say this is the 1 volt and current is leaving the plus terminal, so it is plus, so it is plus 1 volt, okay. So Vs is given, Vs is, you have YB, you have calculator, A you have calculator. So In is coming, In I am writing straight way, so it is coming, if we write the In is equal to minus A matrix, that is minus 1 0 1 minus 1 1 0 0 1, this is the A matrix, then we can write here the B matrix, then here we can write the Vs, and on multiplication we get 1 0. So In is Yn Vn, so 1 0, so we can write here 1 0 which is In, and Yn we have calculated on multiplication. This, so Yn is 1 plus 5 by 11s minus 3 by 11s minus 3 by 11s and 4y11s plus twice s. This is, and there are two nodes, there are two nodes, first and second, and third we have taken the reference node. So this is V1 and this is V2. So this is the matrix. So we can get the B1, B2. The B1, B2, how will get invert this matrix? So if I have one more, so B1 and B2, B1, B2 is inverse of this matrix, 1 plus 5 by 11s minus 3 by 11s minus 3 by 11s 4 by 11s plus 2s, twice s. Take the inverse of this and multiply with 1 0. So we can get node voltages. Okay. So this is the graphical approach using node analysis and mesh analysis to find the response of a complex network. When the dimension of matrix is high, then it will take a lot of time. So we feed the matrices into a computer and you can get the solution, because it is 2 by 2, order of this matrix is 2 by 2. So it is very easy to take the inverse of this. Okay, but when the order of the matrix is very large, so it is a very time consuming process. So we just take the help of the computer and feed the matrices in the computer and to get the inverse in the fraction of second or minutes we get the results. So this is all about your node and mesh analysis using graph theory to find the response of a complex network. So in the node analysis, what we do, we find the fundamental die-set matrix. Okay, fundamental die-set matrix, and then we find the branch impedance matrix and loop impedance matrix we do. In the node analysis, there are two ways. First, either using the reduced incident matrix, that is A, or using the fundamental cut set matrix. Using the reduced incident matrix, we get the node voltages, that is In is equal to Yn and Vn. Using the cut set matrix, we find the cut set admittance matrix, which is the multiplication of fundamental cut set matrix, branch admittance matrix, and transpose of the fundamental cut set matrix. So this way we can solve any complex network using graph theory. So this is all about graph theory approach to find to carry out the node and mesh analysis. So thank you very much. In the next lecture we will start some theorems applied to the AC circuit. Thank you. Jai Hind.